welcome to the n-Lorem podcast series, a series that focuses exclusively on patients now referred to as having nanorare mutations. I'm Stan Crook, and I'm the founder, chairman, and CEO of n-Lorem. n-Lorem is a nonprofit foundation that I initiated in January of 2020. Our mission at n-Lorem is to take advantage of the technology we created at Ionis Pharmaceuticals, Antisense technology, or ASO technology, to discover, develop, and provide experimental ASO treatments to nanorare patients, and to do that for free for life.
Life, mental health, rare disease. That's the focus of Never Give Up, a rare disease podcast hosted by Kevin Alexander. Kevin is an adult living with the rare disease phenylketonuria, or PKU, and for the last decade, he's been active as a PKU, newborn screening, and rare disease advocate. He's also been a professional storyteller for over 20 years. On this storytelling podcast, Kevin shares experiences from his life in advocacy, stories he's encountered while working in television news and video production, and his perspective as someone who lives with a rare disease. The rare disease life can be a heavy burden and can weigh on your mental health, and it can be a lonely life. But when we share our stories, we feel like we aren't alone, and those who hear them feel like they aren't alone. These stories are from one person's rare disease life, stories that hopefully motivate and inspire you on your own journey. Search Never Give Up, a rare disease podcast, in your podcast player to start listening.
Today, we're going to continue our conversations about organs. And today, we'll be discussing your lungs, or our lungs. And the lungs have one main function, and that is to exchange carbon dioxide in blood for oxygen in the air we breathe. Because they are one of the internal organs, and remember, they're called viscera, that are exposed directly to the environment. Lungs have evolved a wide range of systems that protect themselves from the many toxic chemicals in the air that we breathe, and the even greater numbers of infectious organisms that enter as we breathe. If you think about the primary function of the lungs for a minute, you'd probably design lungs that look a lot like the lungs evolution has provided us. You'd want as large a surface area as possible in which air is close contact with blood. And then you'd want to be sure that every air sac, and they're called alveolus. An air sac is an alveolus. Many air sacs are alveoli. So anyway, you'd want every one of your air sacs, or every alveolus, to be adjacent to its own tiny capillary, to assure that every bit of air breathed has as good a chance to exchange oxygen for carbon dioxide as possible. And to make sure that that all happens, you'd want blood flow to be pretty slow going through the lungs, so that you give as much time to every interchange between an alveolus and blood to transfer the oxygen from air to blood and carbon dioxide to air. And that's exactly what lungs do. And it's exactly the way they're designed. The anatomy of the lungs are, like most organs, consistent with the function. So remember that the lungs and the heart are protected by bone in the thorax. And under normal circumstances, most of the power that drives a breathing cycle, that is inspiration and expiration, is generated by the diaphragm moving up and down. But it's also true that the muscles of the chest, and they're called intercostal muscles, also contribute. Since the lungs inflate and deflate every time we breathe, the chest cavity must be flexible. And that flexibility is accomplished by cartilage that connects the ribs to the sternum and the spinal column. Despite the fact that you require this bony structure to protect your heart and your lungs, it's designed so it's flexible enough to allow the lungs to inflate and deflate every time we breathe. You can think then of air delivery system as sort of an inverted tree or grape arbor that begins with the trachea and then branches into ever tinier limbs, ending in these billions of air sacs or alveoli. That architecture is precisely matched to the arborized set of blood vessels, ending in billions of tiny little capillaries matched 1-to-1 with each alveolus. 1-to-1. Every alveolus has its own capillary, and that's critical. So now you have a perfectly matched set of conduits for air and blood spread over an enormous surface area at which the life and death process of exchanging CO2 or carbon dioxide for oxygen takes place many times a minute. This happens so many times in our life. A key point is that the pulmonary circulation, the blood vessels in the lungs, is precisely matched to the architecture of the conduits for air, ending in alveoli or air sacs. Okay, now let's talk about gas exchange. As you know, in blood, you have a specialized protein, hemoglobin, that's housed in red cells with the sole function of exchanging oxygen for carbon dioxide and vice versa as it passes through tissues and into the lung. And the rules are really, really simple. If oxygen is more plentiful than CO2 or carbon dioxide, oxygen displaces carbon dioxide from hemoglobin and vice versa. So as blood flows through tissues, hemoglobin exchanges oxygen for carbon dioxide and other waste. And then that blood is ultimately delivered to the right side of the heart and pumped slowly through the lungs. And since air is rich in oxygen, oxygen displaces carbon dioxide, and the oxygen-rich blood is delivered then to the left side of the heart to be pumped to all the tissues that need that oxygen. It is really that simple. Now, one important detail that should be discussed before we leave gas exchange is surface tension. We've all watched soap bubbles form and then burst. They burst because the surface tension increases as the bubble expands. And you can think of an alveolus as almost like a tiny soap bubble. And it's a matter of life and death to be sure that your alveoli are inflated and do not burst. And to assure that happens, you have a specialized set of lung cells that make a material that lowers the surface tension in your air sacs or alveoli. And that chemical is a surfactant. Any failure to make surfactant can cause alveoli to collapse, making gas exchange impossible. One issue that in the past was a very big problem for premature infants is that the surfactant-producing cells come online very late in gestation. So many preemies failed because we didn't understand how important surfactant was. Fortunately, there are good systems that manage preemies through this issue now, and very few premature infants are lost because they can't keep their alveoli open. Okay, so gas exchange requires a very large surface area in which air sacs or alveoli are inflated when we breathe in. This increases the surface tension and could lead to collapse of the alveoli. And to avoid that, you have these specialized cells in the lung that make this surfactant that reduces surface tension and allows you to keep your alveoli open and available for air to exchange with the blood. Okay, now let's talk about the pulmonary vascular system. That is the blood supply to the lung. You'll recall that I told you the pulmonary vascular system is a low pressure, slow flow system. This is in complete contrast to systemic circulation, with a blood pressure of 120 to 140 millimeters of mercury when the heart beats. The pulmonary system has a blood pressure of around 5 millimeters of mercury, very low. And the pulmonary artery branches or arborizes into these tiny capillaries, and there is a capillary for every air sac or alveoli. So matching blood flow to airflow is absolutely critical to assure that maximum gas exchange happens with every breath. Really critical point. you have to match your blood flow to your airflow at every alveolus to make this whole system work. On occasion, pulmonary vessels constrict inappropriately or have atherosclerotic or other types of heart disease that cause the pressure in the pulmonary vascular system to increase. That's called pulmonary hypertension. And an increase in the blood pressure in the pulmonary vessels is a serious health problem. And it can have very severe consequences, including respiratory failure. To date, treatment of pulmonary hypertension has proven to be difficult. There are patients who, instead of having very low pulmonary blood pressure, have elevated pulmonary blood pressure, and they tend to be quite sick. Okay, key point. The pulmonary vascular system is low pressure, slow flow, and that supports then the fact that for each capillary, there's an alveolus, and that gives time for this gas exchange process to take place. On occasion, some patients have pulmonary blood pressure that's inappropriately high, and this can result in serious, currently difficult to treat consequences for that patient. So the lungs, as I said, are exposed to the environment every time we breathe, and that really produces a set of challenges evolution has worked very hard to address. We have to have complex systems that protect our lung from the air we breathe every time we take a breath. It's obviously vital then to protect our lungs from toxins and infections. And it's also obvious, given the number of colds and flus that we have, that the protective systems are not perfect. So the first thing that you need to protect your lungs from is particulates. In every breath that we take, there are large quantities of small particles that, if they make their way all the way down the pulmonary tree to the alveoli, could do real harm. And the upper airways, starting with the trachea, are designed to remove most of those particulates. There are specialized cells, they're called goblet cells, that make large quantities of mucus. That's one of the big reasons you have mucus, which is to trap these particles. These cells line the airway, and that mucus is designed to trap particulates. There are also cells that have tiny little projections called cilia that move particles up and out of the airways, that is, against gravity. The particles that are most problematic are the really tiny ones. And that's why things like asbestos can cause real significant lung problems and ultimately lung failure, and it can even be associated with cancer. So why do particles in the lung cause problems? Well, first, they're foreign, and they can cause inflammatory reactions that can become chronic, and that alone is a serious problem. The second, of course, they can block airflow. And if they obstruct airflow, then wherever they've obstructed those alveoli, that's a place where air and blood are not matched. And you then have a real problem in managing then gas exchange. Chronic inflammation of the lungs causes what chronic inflammation in other organs is associated with, and that's damage to those tissues and scarring. And that can be called, and that is called pulmonary fibrosis. Okay, let's talk about infections. There are many infectious organisms, and to protect you against the various types of infectious organisms, you have a layered immune response that is designed to protect you. The oldest and most primitive is innate immunity. It is designed to protect us from viruses. Remember that viruses must directly infect your cells and then usurp normal cellular processes like protein translation so that they can multiply and spread. You can think of viruses as little bits of genetic information plus a few proteins that protect the virus and get the infections going in these cells, but then they have to depend on normal cellular processes to further infect other cells and to multiply. Since viruses can be either DNA or RNA, in your cells, you have proteins designed to recognize foreign DNA or foreign RNA and mount a defensive response. And since the lungs are constantly assaulted by viruses, the innate immune system in the lungs is really primed and ready to respond robustly, and typically is responding robustly all the time. Then on top of that, you've got what's called adaptive immunity. The adaptive immune system is a later addition from evolution, and it's capable of mounting vigorous antibody responses and T cell immune reactions to a wide range of antigens. That is, antigens are things that cause an immune reaction. And since bacteria, viruses, and fungi all have some proteins, then they can all cause a vigorous adaptive immune response. The combination of the innate and the adaptive immune systems is remarkably effective if you consider how many infectious organisms are encountered in virtually every breath, and the fact that we're not constantly infected with lung infections. A third element of your protective systems is complement. Complement activation is a very complex process and very tightly regulated. And the reason that it has to be so tightly regulated is that the complement system is designed to produce a whole set of a cascade of reactions that results in actual destruction of different kinds of cells, including bacteria and other cell-based invading organisms. Unfortunately, complement activation is dangerous to the host because once activated, the complement system is pretty indiscriminate and can often attack and cause host cells to be killed as well. So the complement system has many levels of control, but once activated, it creates a cascade of events that often represent a true last man standing type of response. You're in trouble if you get your complement activation going in the lung. A key point: we must protect our lungs from particulates, toxins, or allergic chemicals, and multiple infectious organisms. The respiratory tree has a highly evolved set of processes that do that, but they're hardly infallible. Protection against particulates, toxic chemicals, and infectious agents is required to work every single time we take a breath. If you look at it that way, it's by no means surprising that there are epidemics of respiratory diseases and many diseases caused by toxins in the air. Rather, it's surprising that we aren't constantly sick, that we aren't constantly complaining about lung problems. It's a remarkable system given an enormous challenge. Let's move on and talk about how the respiratory system is innervated. At the most basic level, mammals must have hearts that beat regularly and respiratory tracts that rhythmically exchange carbon dioxide for oxygen. Given the central importance of those functions to life, it's not surprising that they're controlled by the most primitive part of our brain, the medulla oblongata and the brainstem. The lungs are viscera, meaning they're smooth muscle. They're made up of involuntary smooth muscles. Involuntary meaning that you can't tell your smooth muscles to contract as you can your arm. In addition to the smooth muscle that's in the lung, you also have voluntary muscles, skeletal muscles in the diaphragm and the intercostal muscles that have to work together with the lungs to assure that you breathe normally. And so in this case, both your involuntary muscles and the nerves that innervate the viscera or the lungs and skeletal muscles have to work together. And they have to do it with coordination to produce rhythmic breathing. So, why do we breathe rhythmically? Basically, it's the same reason our heart beats regularly. There are specialized cells, in this case, neurons, in the medulla that spontaneously depolarize and repolarize, sending signals to the diaphragm, the ancillary breathing muscles via the phrenic nerve and the autonomic nerves to cause lungs to inspire and expire. You also have enormous numbers of sensory nerves. In those sensory nerves, that is, nerves designed to help us understand what's going on in our environment, there are an enormous range of receptors that constantly monitor the amount of O2, the amount of carbon dioxide, and the pH of our blood, and respond rapidly to even the tiniest changes in those parameters. The roles of each of these receptors vary depending on the levels of the chemicals, that is, oxygen, carbon dioxide, and pH. But for our purposes, any increase in carbon dioxide typically leads to a reduction in pH because you're forming a carbonic acid or bicarbonate and hydrogen ion. Such changes increase the rate and depth of respiration, and increase in O2 does the opposite. So if your carbon dioxide is rising, if the pH in your blood is lowering, you're going to breathe faster. And if you have plenty of oxygen in your blood, you'll breathe more slowly and less deeply. There are also receptors along our respiratory tract response to stretch. If the trachea and the bronchi are stretching, if the lungs are inflating, these receptors identify that fact and can relax the muscles involved. And finally, there's a wide range of chemoreceptors that respond to different chemicals. In the air, it can cause rapid constrictions of airway muscles, and we call those bronchospasms. And in addition to all of that, there are these sensors that can stimulate immune and adaptive immune reactions as well. Okay, autonomic innervation. Recall that you have an autonomic nervous system that's made up of parasympathetic and sympathetic fibers that typically cause the opposite effects on various viscera. In the lungs, the main innervation is parasympathetic. Parasympathetic innervation slows breathing, so you would breathe more rapidly without parasympathetic tone. The sympathetic system plays a role as well. Increases in parasympathetic activity, as I said, slows the respiratory rate. That can constrict the airways and dilate pulmonary vessels. Parasympathetic stimulation can increase mucus production. Sympathetic system basically does the opposite. So you have a yin and a yang on the autonomic system in the lung, just like you do in every other organ, designed to keep a happy medium. Key point: rhythmic breathing is essential to life and driven by neurons that spontaneously depolarize and repolarize. Breathing rhythmically requires collaboration between the autonomic nervous system and the motor nerves that innervate the diaphragm and the muscles of the chest. Now, pulmonary function test, just very quickly. There's a group of tests that can assess various functions required to breathe normally and the ability to move air, the ability to exchange carbon dioxide and oxygen, and the flexibility or compliance of the lungs and chest wall. The whole set of tests that can very, very clearly understand whether you're breathing correctly, and if not, where the problem. To assess the ability to move air, a set of volumes is measured, and the amount of air expired in 1 second is called the FEV1. That is the fraction of expired volume in 1 second. The total amount of air expired within a single breath is called vital capacity, and the amount of air left in the lung after an expiration is called residual volume. Any impairment in the ability to move air will change those parameters. The ability to exchange carbon dioxide for oxygen is measured by evaluating another freely permeable gas, carbon monoxide. And compliance is measured by asking how much pressure is required to increase lung volume. Humans have made lots of inventions that were net harmful to our species, but there is no single human invention that compares to the damage that smoking has done to our species. Smoking does terrible things to the lungs, setting up chronic inflammation and making every other problem worse, to say nothing of cancer and the astonishing array of health issues caused by smoking in other organs. Smoking's terrible, just terrible. And so the key point of this is, if you smoke, stop today. If you're around people who smoke, get them to stop, because secondhand smoke is harming you. If you're in an environment where there is smoking, leave it. Just stop. No more smoking.
n-Lorem is a nonprofit committed to discovering and providing personalized experimental treatments for free, for life, to patients with genetic diseases that affect 1 to 30 patients worldwide, referred to by n-Lorem as nano-rare. Many of these patients progress and die without ever achieving a diagnosis. This is where n-Lorem comes in. They do the impossible by providing hope, and for those that they can help, free lifetime treatment. For more information about n-Lorem or today's episode, visit n-Lorem.org. Any questions can be sent into podcast@n-Lorem.org. Search n-Lorem on Twitter, Instagram, YouTube, LinkedIn, and Facebook to connect with us. Please rate and review the podcast on Apple, Spotify, or wherever you listen. This truly helps us climb the charts and allows others to find the show. This podcast is hosted by Dr. Stan Crook. Our videographer is John Magnuson of Mighty One Productions. Our producers are John Magnuson and Kira Deneen of DNA Today. Thank you for listening.